Dark energy is really the name we give to our ignorance of what's causing the accelerating expansion of the universe.
It's a pushing out that it does. It's a pressure, an outward pressure that the gravitational force is pushing against. Overall, the universe is accelerating in its expansion because of this dark energy effect.
Today, scientists estimate it is overwhelmingly the most prevalent form of energy in the universe.
We thought we knew the constituents of the universe and how it was evolving over time. All of a sudden, we found out that no, we didn't know, because the biggest component of the universe wasn't dark matter, it was dark energy.
So what exactly is dark energy?
And one of the simplest ideas is that it's actually a property of space and time itself.
Scientists had always assumed the energy level of a perfect vacuum was zero. But what if it wasn't? What if, as the universe expanded and created more space, a repulsive energy inherent to that space grew as well? On massive scales, it would oppose and maybe even overcome the gravitational attraction of matter.
And ironically, that's exactly the kind of thing that Einstein had come up with long ago when he was trying to make the universe static.
In his formula to describe the universe, Einstein had added a cosmological constant to perfectly balance the attractive effect of gravity and create his static universe. When astronomers in the 1920s and 30s concluded that the universe wasn't static at all, but expanding, he dropped his cosmological constant and is said to have called it his biggest blunder. But with the discovery of an accelerating expansion, cosmologists revived the term. In fact, it was an idea Adam Rees turned to early in his analysis.
After convincing myself I hadn't made a mistake, I introduced that possibility into the analysis that Einstein's cosmological constant existed, and the FIT grabbed onto it and said, yes, this, at pretty high confidence, this is indeed part of the recipe of the universe.
So how did astronomers miss this most consequential of phenomena?
Perhaps the reason we hadn't noticed it before is because the way you measure it is in terms of how much is it per unit of space-time, perhaps a little chunk of space right here. So you have to divide the entire effect by the volume of the observable universe. So that makes it a very small number.
Imagine the energy released by a match head burning. The estimated equivalent in dark energy is spread across a cube of empty space with an edge about 7.5 miles long, or the amount of space contained by about 1.5 million astrodomes. So it's small, and maybe in the early history of the universe, when it contained a lot less empty space, not even that important.
If we were in a period of time much, much earlier in the history of the universe, dark energy was a very, very small component of the universe, and it wouldn't have necessarily been noticeable.
But that changed about 6 billion years ago. By then, the universe had grown big enough for dark energy to overcome the attractive force of gravity and start speeding up the expansion. Today, dark energy dominates the universe, and it may even determine its ultimate fate.
Now we are in the dark energy era of the universe, which means that the universe is expanding at an accelerated rate.
If the universe would keep on expanding and expanding and expanding,
then we seem to be looking at a far distant future in which the universe is basically empty. It's been diluted of all the other stuff that we otherwise can see lighting up and dancing around us.
Galaxies will just continue moving further and further apart from each other.
our nearest galaxies will go beyond our visible horizon, beyond what we can see in the universe.
Space would stretch even faster than light could catch up to tell us there's a galaxy over there.
Eventually, we will not be able to see the light coming from another galaxy.
We can't see any other galaxy anymore because dark energy and the expansion of the universe has driven this all away. That would be kind of sad.
We might not be sort of torn apart, we just become extremely, extremely lonely.
The end of the universe will be very cold and very dark, and we won't see the nearby galaxies and so on. That's the future expansion of the universe.
If it makes anyone feel better, there is still a lot of uncertainty about dark energy, especially whether it has been consistent over time.
At the moment, we think it's been consistent, but it's potentially Nobel Prize winning if it's been changing over time. And so secretly, not so secretly, cosmologists are really hoping to find something different because that'll be really exciting.
A cosmological constant that isn't really constant could be the solution to another vexing mystery, which some have called a cosmological crisis.
This is a real problem.
There are some tensions in what we're seeing.
This has been a great challenge for us in the last 10 years.
This is something that can't just be wished away.
It has to do with how fast the universe is currently expanding. That's known as the Hubble constant. To calculate it, scientists have mainly used two different approaches. One is based on the baby picture of the universe, the CMB, which itself has been measured in ever-increasing detail.
3 different generations of specially built satellites in the sky to just do this one thing, measure the CMB, to my mind, mind-boggling precision.
The measurements that we have from the cosmic microwave background right now, they are the gold standard in our field. So high quality that when you make measurements from it, they are extremely high precision.
Meanwhile, other groups, including one led by Adam Rees, have calculated the Hubble constant using measurements of distant supernovas.
Distant things from us, but not nearly so distant as the cosmic microwave background. Phenomena that are old in cosmic history, but not quite so old. We call them late universe.
2 different techniques, one based on the early universe, the CMB, and the other on the late universe, using supernovas.
We have the ability to bookend the universe, to essentially see how fast the universe was expanding at the beginning and how fast it's expanding now.
We're measuring the same universe, whether we're measuring the cosmic microwave background or a population of supernovae.
To see if you can go from one to the other, if you can predict how fast the universe ought to be expanding.
And there's all kinds of reasons to think that either one of these kinds of physical systems should give the same answer.
It essentially lets us test our standard model over cosmic time, and that sets up a very beautiful robustness test for, does this model work?
But as the accuracy of each approach has grown, the estimates for the Hubble constant, the speed the universe is expanding, have diverged. A problem known as the Hubble tension.
Many of us are quite fascinated by the implication that we could be missing something still in our understanding of the universe, or this might be another clue about the nature of some of these unknown parts of the universe, the dark matter, the dark energy, things like that.
When we get mismatches, we get pretty excited about it in our field because these tensions tell us that maybe something is not quite right in the model. Maybe that's the hint of where to look for the next breakthrough.
This is where we find new physics. This is where we find discovery.
Is it just measurements being made wrong? Is it modeling being made wrong? Or are we fundamentally not understanding something about our universe? We don't know yet, but it's telling us that cosmology is still very exciting.
4, 3, 2, 1.
So the jury is still out, but more data is on the way. The European Space Agency's Euclid Space Telescope launched on July 1st, 2023. It's designed to look 10 billion years into the past with unprecedented accuracy. And Euclid is not alone in its pursuit of answers. It will soon be joined by NASA's Nancy Grace Roman Space Telescope, which will measure distances and positions for millions of galaxies. But perhaps most fitting will be the work done here, in the soon-to-be-completed Vera C. Rubin Observatory in Chile. It will house the Simone Survey Telescope that will photograph the entire night sky every few nights using the largest digital camera ever constructed.
I think it's wonderful that the Vera C. Rubin Observatory has been named after Vera Rubin. She was fearless and undaunted. She just kept going. My number one belief is that the universe is for everyone. We all have this right to understand our place in the universe and how the universe works. And I think that's really a fitting part of her legacy.